Today, we'll finish a few things of the application layer, and we'll talk of distance vector, which is a very important method for computing paths in networks of all kinds. There is a number of chapters we have not covered in this course, but that's life. This is how things are. There are lots of things that make the story very complicated. But I hope with what we have seen, you're well equipped to discover by yourselves. The topic now is the application layer gateway. An application layer gateway is, by definition, an intermediate system of the application layer. For example, if you go from a web browser to a web server, if there is an application layer gateway in the middle, that means that this system will terminate the TCP connection, will speak the HTTP language, do things, and relay them. Right. This type that I'm showing here with precisely HTTP is called a web proxy, and is very frequently found in companies. So if somebody that's sitting inside a company goes to a web server, then if a web proxy is used, then any object sent by the web server is first sent to the web proxy that then sends it to the final customer. We have seen another name for that kind of systems in the very first lecture of this course. We called it the store and forward system. Right? And we've seen also that the internet was built trying to avoid store and forward. So one of the questions will be, why would we have store and forward things? So this is in detail how a web proxy would work. For example, if you want to get a certain object, this request, if the web proxy is simply acting as a cache, it looks whether it has it locally. If it doesn't have it locally, it will get it from the final destination, store it, and send it to you. If someone else asks for the same object, it's stored locally. Right? That's principle of one of the functions of web proxy. Here, the goal of deploying such a web proxy is to cache things. What's the benefit? Yes?
To avoid too much traffic?
To avoid too much traffic here, on the link between the cache and the system here. EPFL does not have a cache, so many companies do. EPFL does not. Most of the objects today in the internet are dynamic, so caching becomes less interesting. But at the beginning of the web, this was used a lot, in particular because the bandwidth of the links was not so high, so that was a way to trade bandwidth for disk space. You store part of the internet locally here instead of having to fetch it anywhere. Today, the web caching takes the form not of this simple caching that is shown here, but the form of what is called content distribution network, where instead of obtaining and caching data as it is pooled by a customer, instead it's the services that push their content to local replicas that they have in various places. So it's very likely that if you download something from Apple today, you will not get it directly from an Apple server, but perhaps from a content distribution network that has this content for you. The end-to-end principle of the internet is one of the design principles on which the internet was built. Another design principle is to have a unique network layer called the IP. A corollary of this is that whenever you transfer things from A to B, the transfer should be end-to-end, except when we're talking about packets. So it means that any layer that is above the network layer, transport, application, and all the sub-layers that are inside the application layer, should not have intermediate systems. That's a principle. Like any design principle, it's not always observed, but that's one of the ideas that guided and continues to guide the design of the internet. Right? And we have seen why. One of the reasons was to avoid store and forward and simplify improve performance, and also simplify the deployment of new applications. When the web was launched, HTTP and HTML were new, and this did not involve any change in the intermediate systems of the internet because they were just IP routers. So that's the principle of the internet. Now, if we stick to this principle strictly, let's see what that would give. So assume I send you a mail, and you receive it by going to the server of EPFL that has this mail for you. Today, when we download the mail, you go to your server, I go to mine, and the mail servers exchange the mails between each other. So they are intermediate systems of the application layer. So they violate the end-to-end principle. Right? If we would apply the end-to-end principle, how would that work? How would email work? Yes?
We directly contact B and send it whatever you need to send it.
Exactly. A would directly contact B, so you will have an SMTP kind of daemon here on your PC or on your smartphone, and there would be a direct connection between A and B to download the mail here. This is not done, or practically never. Why? Yes, computers are not always available on the network. So it was done in 25 years ago when the computers were workstations that were in a special room that were always connected. Today, it's probably most computers are turned on and off when you don't need them, hopefully, to save energy. And they might be mobile, so you might be moving around, you might not be connected. So for simply availability of the connection, this is a sufficient reason for not doing it. Yes?
Also nowadays, it would be complicated to find the IP of the person you want to talk to, right?
You might have a problem to find the IP address of whom you talk to. That's correct, but that's what we do if we use Skype.
True, but when you're on Skype, you know that the person is online, so you can get his IP from...
Yes, but if A and B, if this is a Skype session, not always, but in most cases, Skype will try very hard to not use intermediate systems because Skype is not interested in running hordes of servers that forward the voice packets for you. Plus, they're encrypted end-to-end, so they're unusable. So Skype is not doing that. If you're using Skype to communicate from A and B, there will be no intermediate system for the transfer of voice or video or the images. But there will be an intermediate system for establishing the call. So you will call to the Skype infrastructure. B will speak to the Skype infrastructure. You will know that both are online because you have a heartbeat system that once in a while you send a message to Skype, and then Skype knows the two IP addresses of each of you. And if the firewalls or the NATs that are between you and the internet are not too nasty, those IP addresses will work. So A will be able to call you on the IP address that is the IP address visible from the Skype server. Some NATs do very tricky mappings, so they may give a different address depending on who is talking to you. Those NATs will cause trouble to Skype and will force Skype to have an intermediate system. So what we've discussed here is practical reasons that make intermediate systems necessary. So the take-home message is the end-to-end principle is a principle that is generally adhered to. If you don't adhere to it, you probably should have a good reason for that, and we have seen that there's a number of them, right? I mentioned that if you go to companies, most of the time you will be behind a firewall. For example, that's one experience I did. I was sitting one day at a meeting at Romande Energie, then I went over the internet to look up for something, and the page I received was this one, right? It was saying to me, I was going to a website, a number of websites worked, and one of them did not work. And I got a message like this, right? I was looking at a perfectly legitimate site, nothing exotic, but Romande Energie thought that somebody who's working in their premises has no reason to go to this place, right? Perhaps I was watching what's the TV program or something like this. And there's no reason to do that. Which means here there was an intermediate system of the HTTP protocol, of the application layer. Whenever I go to a website, I was first going to a web server of Romand Energy that then goes to the website for me if the policy of the application layer of web browsing at this company allows it. And here there are very strict rules. There are lots of things they don't allow because they want their people to work and not to spend their time doing other things. So that's one of the reasons we had mentioned usability being available online. This one is access control, perhaps also security, making sure you don't go to websites that are more likely to contain viruses, although you don't really know which websites will infect you. So this is one of the reasons for having intermediate systems. Another reason is load balancing. That's a very, very frequently deployed set of systems. Most of us, when we're on the internet, we see small side things, but most places we go are data centers. Data centers we've seen already when we talked about data center TCP. So there are rooms full of PCs that number crunch all the requests you're sending to them. And one of the issues for data centers is to do the load balancing inside the data center. We have seen already a form of load balancing across multiple data centers. If a company like Google has 50 data centers over the world, they want you to go to one of the 50s, depending on the load on the servers and perhaps also your distance measured in RTT to those servers. But we have seen that this is best done by DNS. So by having multiple names and very, very short time to live in the DNS, it's one way to load balance across data centers. But now once your request, or those two requests have come to this center, you need to allocate it to one of the machines. A simple way to do it, which is practically invariably deployed, is that the web server, the application, is terminated in a first system, which is called a load balancer, that simply gets the first message of any request you're sending, and then picks one of the servers and sends it to you, and remembers the server to which it was sent, if this is stateful, or uses hashing methods to make sure that you always go to the same server. If this is a slightly different method, there's a number of load balancing algorithms that have been derived here. So I mentioned how this can be done. So one of the ways that Lisa goes to this computer and Bart goes to this one is, for example, to do like a NAT does, but except a NAT chooses simply port numbers. Here you can choose also destination IP addresses here. Those two load balancers have the same IP address from the viewpoint, from the outside. Of course, they have other IP addresses to talk to them internally, but to the outside here, they both are at the same IP address. So when you go to the DNS, you will see one IP address, you will not see that you're talking to two different machines. And here, when you get into the data center, you will have a form of routing with OSPF. We've seen, for example, we can do something called equal cost multipath. So we can have two paths to the same IP address. In this case, it's not because we have two paths of equal cost that go to the same physical machine, but here it's because we have two paths that go to different machines that both pretend to be the same IP address. So through this mechanism here, you may lead to one of the two load balancers, and that will take care of the reliability of having more than one load balancer. In particular, if one of them dies, and if we have a way to very quickly detect that it's dead, for example, if the load balancer participates in the routing protocol, participates in OSPF by injecting its presence or not in OSPF, if it's dead, then the routing infrastructure, he will detect that it's dead and will have only one place to send it to. And of course, you can imagine having more than one place. So that's another reason for having intermediate systems. And we see that this is combined with things like DNS load balancing and equal cost multipath here. I mentioned Roman d'Energie blocking us from going directly to the internet. They probably have something like this, which is called a firewall. So this is a very typical setting that you have when you access the internet from inside a company. Here, you have web or other web proxy or other machines that can also serve as load balancers. And those machines are isolated both from the interior network and the outside network by routers that have very strict filtering rules. You may remember that we have seen in some of the exercises that we can manipulate the way the routers work. The routers normally do the IP forwarding, but with SDN or other mechanisms, we can implement rules, access control lists, and other mechanisms to decide, for example, that no one here should have a web server. Right? There's no reason for somebody inside Roman d'Energie to run a web server in their computer. So if anybody is trying to open a TCP, sending a TCP SYN packet towards an HTTP port, or probably even any TCP SYN packets to any machine here, this will be blocked by this computer, by this router here. This router will allow TCP SYN packets, but only to one of the machines that is in this zone here, which is sometimes called the demilitarized zone, the DMZ. So it's the idea that you create a zone that is under the control of the people who know, hopefully, who are the network managers of the company. So if you want to go to the internet, or if you want to publish something, any interaction between the outside and the inside must go through one of those machines. So those machines are more likely to be up to date in terms of software, antivirus, having the latest version of all the crypto software to avoid any kind of problems, which is more difficult to enforce for everybody's computer. Another reason for having intermediate systems, which is quite widespread, in fact, very likely when you go to anywhere today, you go through such systems. Quick question. When we are in a setting like this, how many TCP connections are there on this figure? We have 2 users. Every user uses a number of TCP connections to do the transfer of one object. How many TCP connections does that give in total? I close the poll. And the majority says 4, which is obviously the case, which is the correct answer. Here there's one TCP connection between Lisa and the load balancer, and another one between this and the server here. Of course, there might be other TCP connections if you do map reduce or distributed computation. Yes?
Could you give us the number of...
Oh, I'm sorry. Yes, I realized there was not so many answers. With which system do you need to get the number? Android? iOS? Four, 6, 3, 6, 5. Who could see the poll without number? On laptop, on computers, web browser? iOS? Okay. Here, the TCP connection is broken here, which of course means the load balancer has a heavy work to do. Yes?
But how can you be sure that the load balancer will use this connection to talk to the data center?
Oh, we don't know. We don't know. It's typically the case, but we don't know. But most traffic in the data centers is over TCP.
That means
Yes, yes, yes. The incorrect answer would be to believe that it's end-to-end here. Right. So that is something you want to avoid inside the internet. Sometimes this is used also for performance reasons. Might be another reason to have intermediate systems. Can you imagine a case where breaking a TCP connection between two and having an intermediate point that simply copies everything it receives on one TCP connection onto the other? So it does nothing. The semantics of it is nothing. If we want to write socket program to do that, you simply read everything that comes on one TCP connection and you write it into the next. So you have a constant loop, read 1 byte. For every byte that you could read, you write it into the other connection. That seems stupid, but there might be cases where there's a benefit. Can you imagine one? Well, one case is to try to mitigate performance problems of TCP. There's one case where TCP will not work very well. It is if you're accessing a server that's far away, you have a large round trip time, and you have losses that are not due to congestion. For example, because you're mobile, you're surfing the net while cycling, and or even on a bicycle, on a car. So the radio channel is subject to fading. Once in a while you may lose a packet. If that happens with probability 5–10%, we know your throughput will be very bad. Plus, in addition, your round trip time is very large, so you're competing very unfairly with the rest of the world, so perhaps your transfer time will be very, very poor. If you put a TCP proxy in the base station, then of course you will still have the losses, but you won't have the round trip time problem. So you will have, between you and the base station, you will have one TCP connection, and if you're doing that over a cellular network, you're competing with no one. Typically, once the channel is established with some quality of service, what I said is wrong. You are competing with others, but once a channel is established for you, there is some control of how much bandwidth you will obtain. So if you have lots of losses, that doesn't mean that others will get more. The cellular networks typically implement some form of rate control that is per customer. So then the losses will not dramatically impact the transfer rate between you and the proxy. And between the proxy, which is in Swisscom's premises, and the rest of the world, then this is high speed and high quality, so you'll have high speed transfer. So this might be one of the reasons to break TCP connections. And it's routinely done, in fact, by cellular operators. And this is one of the reasons that changing TCP is very difficult to do. This is one of the motivations for QUIC in particular. We'll talk now of one of the very interesting topics that we would do if we had more time, which is the transition to IPv6. That's one of my preferred topics. I've been teaching it for 20 years. 20 years ago, I said in 10 years, we will have to finish the transition to IPv6, and that was 10 years ago. It's not yet finished, so I don't, to be honest, I don't know. IPv4 addresses are exhausted. You can't have any more new IPv4 address. So if you want to do anything, any new development, you have to have new IPv6 and you want new addresses, you will have to have IPv6 addresses. You'll have to do things for IPv6. Except there's still one way to escape IPv6, which is there's lots of IPv4 address that everybody can use and will be able to use for forever. Which ones? The private. The 10 dot addresses. You can build a huge network with 10 dot addresses. As long as it's your own private network, it's fine. And so that's one of the motivations for slowing down the migration to IPv6. Nonetheless, I'm still optimistic. We see a lot of movements towards IPv6. For example, any new iOS application, if you want to publish your app on Apple's store, it has to work for IPv6. Right? So if it works only for IPv4, it will not be accepted on iOS. Android accepts it, but iOS won't. And one day Android will say the same, and then from that day on, everything will have to be IPv6, except a few things like industrial networks, the network that is used by the railway company to control the signaling system, the lights and the switches, might still be IPv4. So we will have, in any case, the need to coexist, to manage the coexistence of IPv4 and IPv6 here. Here is one of the things that, as an application, if you run an application and you connect to a remote destination, we know that from the lab 3, from the programming lab, that you need to do something to be, either you use one of the constructions in Python or other languages that are independent of IPv4, IPv6, but we've seen they're a bit complicated. And those constructions, in fact, are just intermediate layers that hide from us the need to choose from IPv4, IPv6. So in the software, at one point, you will need to choose. And this is because, as we have seen, IPv6 is treated by the operating system, by the IETF, by the internet community, as a different protocol than IPv4, not as the same protocol with a different address space, like we do, for example, when we do BGP, and we've extended the AS number from 16-bit to 32-bit, we did not create a new incompatible BGP. We kept the same BGP, and then any new version of BGP that is not able to handle the 16.4-bit addresses will not work. So there's a strong incentive to make it to work. IPv6 did not choose that for some reason. So if you want, in Bitcoin terminology, IPv6 is a hard fork from IPv4. They are completely independent here. Which poses a number of problems. So if you have a modern device, you probably have both IPv4 and IPv6. And now if you go to a website, lca.epfl.ch, this one, which is in China, or InfoScience. InfoScience is on IPv4 only. And one of the reasons seemed to be that to have access to some libraries that EPFL subscribes to, the access control is done based on the IP address. So if you go to IEEE Explore, it checks whether your IP address is an EPFL address, 128.178/15. If it belongs to that block, it allows you, otherwise not. And obviously, the people who do that, even if they're IEEE, they don't know that IPv6 exists. So you can access InfoScience only with IPv4. This is the website of our lab, and this one is both IPv4 and IPv6 that we tried. And if you build a new thing somewhere, you might have IPv6 only. So how do we know? How will Lisa know whether to use IPv4 or IPv6 to connect to either of it, right? Don't be influenced by this red circle. This is a false hint. What do you think? Okay, let's close. And the majority thinks as the hint is, so let's discuss. One way would be to send a ping. You want to connect to something, you send a ping. But that's not a good idea. Why? It's not that a bad idea either, if you don't know, before talking to a web server and knowing whether that web server exists, sending a ping causes much less work to a web server than opening a TCP connection. So if it, yes?
So if everyone thinks it, it might look like a DOS attack, I guess, and it will stop answering?
Yes. So one of the problems is it works if it works, which means if the web server accepts to receive pings and responds to them. Many web servers don't, because that might be denial of service attacks. There are some robots that are widespread and do that kind of things. So many systems block the pings. Not all, but many do. So if the absence of ping doesn't mean that IPv6 doesn't work, for example. This would be feasible. You can try both. And in fact, some applications do that. I mentioned Skype a minute ago. When A and B connect via Skype, there are zillions of possible cases that can happen. I mean, both can be on IPv4. Both can be on IPv6. There can be a dual stack IPv4 v6 and the other is IPv4 only, or the other is IPv6 only. Or even worse, you're IPv4, but you're behind a NAT, and in fact you're IPv6, and the NAT gives you an IPv4 address. I mean, all those combinations are possible. So what Skype does is try everything. So that's the Skype approach. Skype does that kind of things. It will try to send lots of different ways to contact you and will eventually settle on the less expensive for Skype, the one that works natively and requires as little transformation as possible and does not require Skype intermediate servers to be involved in the communication. But if you do that in HTTP, that is clearly an overkill. So whenever you connect a server, that means you try both. And hopefully you hope in the long run you will be v6 only. So the question would be asked, when do we stop doing v4? Right. So the correct answer is none of the above. And the answer is we use DNS. Right. The first little thing to observe about DNS is that DNS is a database of mappings of names to IP addresses, and it can be reached with IPv4 or IPv6 for questions that are IPv4 or IPv6. So if you want to get an IPv6 address, you don't necessarily need to speak to a DNS server using IPv6. So the two are independent in principle. So Lisa's PC has it must have a DNS server. Here it's running only IPv4, but what Lisa will do, it will ask to the DNS server, to that name, what is the IP address? And then it will ask both, because we consider it's not too much work to ask a server to get both records. It's much less work than try to connect to a web server twice here. So Lisa will ask for both and will get both addresses or only one. Here it will get only one. You will get an IPv6 address, so it will connect using IPv6. We find here an interesting use of DNS. It was not at all anticipated at the beginning. DNS was here just for human readability and convenience. In fact, now DNS plays a central role in IPv4 versus IPv6. It's really DNS that's one of the central elements in being able to handle both. We've seen that DNS is also used for load balancing. So those are useful features that come after its invention. Now, if we continue the story, we will certainly be confronted with cases like this one, where you have somebody speaking IPv4 and someone else speaking IPv6, and if both can speak only this, they can't talk to each other. There is no communication possible. So what do I do if I have an IPv6 only host and I want to connect to InfoScience? That's the question that we're addressing today. That question is called interworking. How can an IPv6 only machine talk to an IPv4 only machine? And both cases can exist where you can put the server on IPv4, and that means you have an old style server in a region of the world that has only IPv6 addresses. That happens, for example, in regions of the world where you will access the internet over IPv4, IPv6 cellular services that will tend to give you IPv6 addresses, and you want to access InfoScience. How do you do? And this is what we will discuss now. What we will not discuss now, and we would have discussed if I would have had a bit more time, is the like-to-like access. Like-to-like access means how can IPv6 talk to IPv6 when the path between them is not entirely IPv6. Right? That happens today if you have an IPv6 only machine that connects to an IPv6 server, but your internet service provider gives you IPv4 only. At home, you can easily run IPv6 by letting your ADSL modem and all your equipment run IPv6. But if Sunrise or Swisscom gives you only an IPv4 address, you're stuck. Right? So this problem is less severe. This problem is how does an IPv6 application talk to an IPv6 application over an IPv4 infrastructure. And the converse will be true also in a distant future when you will have islands of IPv4 legacy systems. For example, a telephone in a lift, an IP telephone that was done with IPv4 because the people who developed it were not so smart. They didn't think of making it IPv6. And then the world is IPv6 only. This is solved by what we call tunnels. A tunnel is a complicated name for something very simple, where the idea is you can carry an IP, in this case here, you can carry an IPv6 packet inside an IPv4 packet. So we can treat IPv4 the same way that IP treats MAC. When A talks to B and they're connected by Ethernet stuff, Internet layer puts its IP packet into Ethernet packets. Right. Here we can do the same. If I am at home with IPv6 only, I can have a device, that's the end of a tunnel, that will encapsulate, put all my IPv6 packet inside IPv4 packet, and then you need to find a way to reach the destination. The management of the tunnels, that's the topic if you do this. That's the essence of the solution here. Here, the problem is different. Here, my machine speaks only IPv6. I don't have an IPv4 stack. I do not have IPv4 sockets, but I still want to go to InfoScience. Right? How can I do that? It's a more difficult problem. It's called interworking. And there is a very simple solution, which is intermediate system of the application layer, which consists in saying, if I am IPv6 only, then I must find somewhere an intermediate system that will do the job for me of converting IPv6 to IPv4. And this can be if I'm connected to a provider that gives me only IPv6, this will be typically one of the services that the provider will give you. So this very simple way consists in having connecting, instead of connecting the final server, I will connect to the web proxy. I will send my HTTP GET request or my TLS packets here, and then they will be simply re-forwarded to the final destination. And since this one can do both, it will, the problem will go away. This is what is done, for example, at EPFL. If you go to www.epfl.ch, which is an IPv4 application and IPv4 machine, it's also reachable over IPv6. But if you do a Wireshark and observe in detail what happens when you go over IPv6, in fact, EPFL has simply set up a proxy, a device that responds to this name under IPv6. So if Homer, which has only IPv4, wants to go to this site, what will Homer do? Or Homer's device? It will go to the DNS first. So we find again the DNS playing the central role. It will go to the DNS and ask what's the IP address of this. And it will ask what's the IPv4 address because it's an IPv4 only host. And if there is no answer, then it's Homer is stuck, cannot connect to this service. But here there will be an answer. The DNS will have an entry for this machine, which is another machine of EPFL, which has also the name www6, epfl.ch, and this IPv6 address. And for Homer, this is the web server of EPFL. But in fact, this is not the real web server. That's simply a repeater or an application layer repeater. Whenever Homer sends a request to this machine, it is immediately forwarded to this one over IPv4, here, using one of the principles we've seen before. So that's another use of application layer gateways that is now solving this incompatibility between the two here. Right. Now, if someone else is using IPv4, then by going to the DNS and asking the question, you will get the native IPv4, the address of the native web server, and you will go directly here. And now one of the questions we might ask, I'll skip those questions. We see here, for example, that if I'm using IPv4, I have a better service than if I'm using IPv6, because by using IPv6, I will always go through an intermediate system, so all my requests will be a bit longer. My RTT is longer, I have an intermediate system, but in this case is not improving performance. It's improving functionality, but it adds an intermediate system and makes the performance a bit less good. One of the questions we might ask is, what if I have both? So if I have now a machine that has both IPv4 and IPv6, what will happen? Can you guess? If we reason a bit, we see that if this machine is both IPv4 and IPv6, it will go to the DNS for this, it will ask both, and we'll get two answers. We know, because we are behind the scene, we know the best answer is this one, because that's the native machine. You go there directly instead of going through an intermediate system. But this one doesn't know. So what will happen? Well, the answer is, in reality, it depends. We've done a number of tests, and some machines, for example, my Windows 7's PC, systematically prefers IPv6. And many machines did that in the past because they thought if you have both IPv4 and IPv6, IPv6 is the most recent one, it must be that the true thing is there. IPv4 is there for simply compatibility, which in that case is perhaps not the good answer. Other machines, like Apple's Macintosh operating system, tries to do better heuristics by trying to, once in a while, to try one, try the other, and keep a record of what works best. But that's one of the true problems here. If you have both, probably one of the two is the right one and works better, and you would like to move quickly to that one. In the long term, it will always be IPv6. In the medium term, we don't know, and it really depends on what your operating system will do, and a given operating system tends to change depending on experience gain here. Well, I will skip this one. Yes. That's all we will say about the application layer. Of course, the application layer is perhaps the most fascinating part of the internet, but to understand how it works well from our perspective, from below, I think it was useful to go through all the things we've seen here. So remember that applications have to choose UDP or TCP and must be able to use both IPv4 and IPv6. And remember also the central role that the DNS plays into deciding which place we go to, and in particular also which networking stack we use, IPv4 or IPv6. Voila, we do a break, and after the break we will talk about distance vector, our last topic of the year. We're ready to restart? So we go back to routing. Distance vector is one of the methods we have discussed already when we gave an overview of all the routing methods. What's the difference between distance vector and link state routing? Link state routing is link state routing is relatively naive in the sense intellectually, in that it distributes a map of the entire network. Distance vector is much more compressed. It does not distribute a map of the entire network. The analogy is really the road system. If I follow the signs indicated on the road system, I can go to destinations that are far away simply by knowing at every intersection which way to go. I don't need to have the entire map. Of course, I have more control on my trajectory if I use a map, but if the goal is simply to get there, I can have less information. That's the idea of distance vector. So distance vector is very old. It's practically as old as computer networking. Link state routing came much later. Why is that? Because distance vector is much more efficient in terms of memory usage and processing power required by the routers. And we'll see it's a generic method that can be used in a prototype of a mechanism to distribute connectivity. What it does, like link state, it computes shortest path to all destinations using distributed Bellman-Ford. And the key thing is here, the only information, at least in the simplest form of distance vector, the only information that is strictly needed is the distance from self to all destinations. That's the destination from a node to all possible destinations. This information, we can put it in the routing table. So if we add in the routing table the number of hops to the final destination, we have the only information that is needed by distance vector. That was the initial idea of distance vector, is to use only that. If you compare to OSPF or BGP, they have RIBs, routing information base, that have a lot of information about the network, not just this here. In its simplest form, distance vector routing doesn't need a RIB. It would need only the distance from self to all destinations. To be able to work, you need to use one specific shortest path computation algorithm, which is this one, is Bellman-Ford. Link state routing typically uses the generally most efficient shortest path algorithm, which is Dijkstra's algorithm. Here, it uses a different one. Dijkstra computes the shortest path from self to all destination. Bellman-Ford does the opposite. It computes the distances from anywhere to one specific destination. So if you want to run it in reality, you have to run n parallel instances of that, one per destination. We will see how this is done in practice. So here is the simplest form of the Bellman-Ford algorithm. It's centralized. So it's meant to be run in a central server, which of course is not what is done in distance vector. If we have a central server, it means we can connect to all nodes. So then we use probably Dijkstra. But here, to understand how distance vector works, it's better to reason first on the centralized versions. This centralized version loops does an iteration over an index k, and at iteration k, it computes an estimate of the distance, pk of I, which is the distance from node I to a specific destination. So the specific destination, I call it here node 1. So we compute all the distances from everybody to node 1 here. And it's done by this. So first, initially, I say node 1 is at a distance 0 of itself. So I do this. And all other nodes initially don't know. So they put distance equal to plus infinity. Infinity here will not induce not a number kind of results. There will not be any indetermination because we do only additions. So we don't have minus infinity. So then at iteration k, it does the following. I ask what was the result of the previous round, and I say my estimate of the distance from me, I, to 1, is the minimum of the distance from me to any j. Of course, it's only the j's that are neighbors, because otherwise this cost is infinite, so we don't need to consider it, and it will never reach the minimum. So I look at all possible neighbors that have j. I calculate what is the sum of the cost of going to this neighbor. That's the cost of the link. This must be configured in distance vector routing, like in OSPF or in any routing protocol, plus the distance of going from this neighbor to the final destination. So I try all my neighbors. I add my cost to go there plus their cost, and whatever is the smallest, I take as my best guess here. And that's the end of iteration k. At iteration k plus 1, I will take the result of this and hope it finishes. And if it finishes, we return the result. It finishes when it's stationary. Stationary here is a strict concept. It means it really does not change. When we've reached a point where the output of this is the same as the input, then we stop, because of course this is a recursive computation. Here, this block of computation is simply modifying p, taking as input p itself. So if we found two values of p that are the same, the algorithm is now stopped. It will do the same forever. And the hope is that it will converge, and at convergence, it will give the true destination. So let's see an example. Here one is this node. I've put all the costs on the links. And here are the estimates in the boxes, are the estimates of going from this node to the final destination. So at iteration 0, they're infinite everywhere, and they are 0 at the final destination. At iteration 1, what do we do? Well, if I am node E, for example, I ask all my neighbors, I have 3 neighbors, what was your cost in the previous iteration? In the previous iterations, they were all infinite. So my cost of going from there, I add the cost plus infinity, it gives infinity again. But if I am node D, for example, I ask all my neighbors what was the cost in the previous iterations. They're all infinite except one that had a cost of 0. So I will take 5 plus 0, that gives 5. So D now has an estimate of 5. And similarly, B has an estimate of 1 here. C and E have still estimates that are infinite here. One useful way to think about this is to think of it as a message passing interpretation. We can view it as a loop, like I said before, but instead we can say when I do this, it is the same as if I focus on node D, D asks all of its 3 neighbors, give me the value that you had at the previous iteration. Give me your value. So if E passes a message to D with its value, then D will be able to update using this. And if we do this synchronously, we do exactly the same as this algorithm. If we do that asynchronously, so if messages are sent whenever we have time to send them, then you obtain exactly the distributed version of Bellman-Ford, which is the one used in distance vector. But before getting there, we need to analyze some of the properties of this algorithm to understand why asynchronous message passing works well. So here I've done the following iteration. So at iteration k equal 2, we see that C has now, by asking all of its neighbors from the previous iteration, it has found a distance of 7 because the 2 best neighbors are B and E, 1 and infinite. So it has found a path or a distance that is 7 here. Right. If we continue this, if you continue this, will it stop? And when will it stop? So I'm asking you to be a computer for a few seconds and run this algorithm to see when and if it stops. I close the poll. The majority says 4, which is the correct answer. So we can do the simulation, and we'll see that here we don't change. And then those are the values here. We can do lots, we can see more things on this. Can you interpret what was computed here, for example, at k equal 2? What did we compute? What did the number 7 represent? It's not the final distance. The distance from C to 1 is 4. But 7 has a meaning. It's not just an arbitrary value that the algorithm was taking. It is something, yes?
It's the smallest value after 2 steps. So after 2 paths.
It's the smallest value in up to 2 hops. So if we allow to go from C to 1 in at most 2 hops, the best we can do is 7. If we now allow 3 hops, we will get a better path here, which is 4. And since the best path is in 3 hops, it stops here. In fact, we can easily show by induction that with those initial conditions that are given here, this algorithm does exactly that. At iteration k, it computes the distance from anywhere to the chosen destination in at most k hops. And then it's clear, then the distance at most k hops from this follows from this update here. If this is the distance in up to k minus 1 hop, then in at most k hops, then I have to look at all my neighbors, look at what they've done, and pick the best here. So this is why it works. So of course it will stop. The algorithm will stop. It will stop in a number of iterations that is certainly upper bounded by the number of hops over the longest shortest path, which is upper bounded by the diameter of the network, which is upper bounded by the number of nodes. So this algorithm will certainly terminate in a finite number of steps, and when it will terminate, it will have the correct values. Another thing we can observe is this, we can find the shortest path here. So here I've written the distances, the final values, 4, 1, 0, 3, and 3 here. Assume now I give you only those values, so the values that are written here in the boxes. Then I claim that using only those values, every node is able to compute where to go in order to reach node 1. What is the direction of the shortest path? For example, if I am node C, I can do the following. If I know that B is at a distance 1 and E is at a distance 3, I know that I have only neighbors B and E. I will test my two neighbors. I'll say, if I go through B, then I know the distance from B to the destination is 1. That costs me 7. If I go through E, that costs me 1 plus 3, 4. So the shortest path is via E. So by examining, running a computation that's similar to this one, which consists in computing the mean of this plus the P, the final P, and looking for which J we obtain the mean, that gives us also where to go. That's the second information we get from this, which is encapsulated in this theorem. The theorem says that it works. If the network is fully connected, it stops at the latest at n, but in practice much less, and outputs the distances, the correct distances. At iteration k is the distance in k hops, and we can find the next hop along the shortest path from node I by looking for which j minimizes a of ij, the cost of me to j, plus the cost from j to the final destination. So that is the first thing we can say. However, I would not like you to keep these ideas too deeply rooted, because as we will see, everything that is said here may not always be true when we really do that in a network with distance vector. So this we have said here. In particular, we should address the following question. Everything I said before works well if we have been running the algorithm with clean initial conditions. And the initial conditions are everybody knows that my final distance is infinite, that I am not node 1, so my distance is infinite, and one knows it is 1. If we run that in a network, that means we would need to run it either in a centralized node, or if it's distributed everywhere, we've seen that we can do something which is probably the same by having every node compute their own value and pass it to the neighbors and ask the neighbors to pass it to them until it converges. We could do that. But if we do that, we're confronted with the problem of changes into the network. What happens if the network has been running for some time, everybody has computed the distances and the shortest path, and then something changes? Why would there be a change? Well, that's typically a failure or addition of a new node. A link breaks, a router crashes, or the RIPD daemon crashes and reboots. The goal of routing protocol is to be able to adapt to any change to the network. Adaptation to this, if we run it in a distributed way, poses the question, Should we detect that there is a change and reset everything, or should we simply continue the computation? In OSPF, when there is a change, we actively delete. Every node sends new LSA that gives it all the networks it's attached to. So that replaces the old value. So we delete the old information. And whenever there is a change, every node does a fresh computation of the shortest path. So it recomputes all the shortest path. Here, if we do that distributed with every node knowing only its distance to destination, then it could be that it is equivalent to running the algorithm with initial conditions that are wrong. The initial conditions are simply the values to which the algorithm had converged before the change. For example, here, perhaps this link was down, and B had a very long link that was at a cost of 10, and there was another link, a very good link, from C to 1 that had a cost of 1, and this link that was down is now going up, and this link that was up is now going down. So there might be changes in the network, and the question is, when there are such changes in the network, can we simply continue running the algorithm, ignoring that the change has occurred? If we can do that, that's miraculous. That would be wonderful. Because that means if one link somewhere crashes, the nodes continue doing the same thing. They don't need to know that the link has crashed. They will update the thing. If this doesn't work, that means when a link crashes, we need to inform everybody to restart their computation, which is more or less what OSPF is doing. So in order to know what we should do, we need to understand this. If we run Bellman-Ford from those conditions, what will happen? Guess. I close the poll in 5 seconds. And we almost have a tie between A and C. Well, let me hold the correct answer for a few seconds. Let us examine this example in detail. Whoops. Let's run the algorithm on this example. So we run the algorithm with those initial conditions. Those initial conditions, they look very bizarre and stupid. They have nothing to do with the physics of the network, but let's take them as granted. So what will happen at the first iteration? We can interpret that as a message passing interpretation. So B will say to all of its neighbors, my distance is 10, okay? So E will hear from B, the distance is 10, but E will also hear from D, the distance is 10, and will hear from C, the distance is 1. So those two will lead E to think, it will take the minimum of the distance from itself to the neighbors plus the distance known by the neighbors. So there is 1 and 1 here plus 1 that gives 2. So E will believe it is at a distance of 2. Here, same thing for D. D will receive from B the distance of 10, which is not very interesting. From E, it will hear, oh, it's a distance of 1 plus 1, that's 2. So I am at a distance of 2. So this is what will happen, and those are the values we will obtain here. If we continue, we see that it changes according to some more or less random pattern, and miracle here, the same thing happened, it stops and converges to the correct value here. So on this example, it converges to the correct values in spite of completely abnormal initial conditions. It converges, but what we have lost is the interpretation that at iteration k, we are computing the distances in at most k hops. This is certainly not true here. Well, here it's true, but here it is not the distance in at most k hops. We see that the distance here, if we look at C, it is increasing 1, 2, 3, 4, whereas the distance in at most k hops, when we increase k, this distance must decrease. So this interpretation of Bellman-Ford is no longer valid with those initial conditions. Let me skip the question to save time and go directly to the answer. This was in the case where the network was completely partitioned. So it seems, at least on this example, that if we start from arbitrary bizarre conditions, miracle happens, it will still converge to the correct value. And then understanding why is more complicated. It's not because there was this interpretation in at most k hops. It's a bit more abstract. But it is true, at least on this example. Now here's another example where a change happened in the network that is a partition. That happens also in a network. So assume here C and E are broken from the rest of the network. You could tell me this is impossible. Double failures happen together with probability 0. But this is perhaps very unlikely, but not so unlikely. Can you imagine reasons for having a double failure?
BGP failure?
It could be BGP, right? It could be a single failure of something else. Here it could be because they talk together because they use BGP, but perhaps BGP did something wrong and they failed. So it could be the failure of something else, which is another protocol like BGP. It could be that they are connected by a switch of some kind and this switch is down. It could be that they are not connected by a switch. You have point-to-point links, but the point-to-point links are optical fibers that are multiplexed over a wavelength division multiplexing infrastructure, and the optical multiplexer is dead. Or even worse, they are truly separated physical optical fibers that use everything is physical, but they are in the same plastic pipe buried in the same street. And this street was cut by a caterpillar that's doing road construction. So you can, there's lots of famous examples in past histories of disconnecting networks by things like this. One example was a fire in a tunnel close to the Boston airport where the tunnel, everything in the tunnel melted, including all the communication links of multiple operators. So if that happens, what will Bellman-Ford do? Then we can zoom on C and E. C believes that it is at a distance 4 of 1, which is of course completely wrong. It's at the distance, the true value is how much? Infinity. It's not connected to 1, so the distance is infinity. So C will ask E, what's your distance? 3 will say 3. E will say 3, okay. So next iteration, C will say 4. Similar, E have asked C and say, what's your distance? 4. So E will say, I'm 5. Okay. Next round, each will ask, and they will now obtain 5 and 6, 6 and 7, 7 and 8, etc. What will happen? They will continue doing this ping-pong game. They will increase their distances, so the algorithm will not converge. It will go to infinity, which is in some sense the desired behavior, because the true distance is infinite. So in a case like this, the algorithm converges to the correct values in this connected area, but it counts to infinity at C and E. So this is a known behavior of all distance vector protocols. When two nodes are not connected to when there is a partition, the distance vector routing protocol will count to infinity, which you could say academically is the right behavior. It's going to the true value. But practically, what will your router do, right? It's caught in an infinite loop that will never stop. What would you do to block this count to infinity? You set a threshold, exactly. So if you're in a network that has a size which is a diameter that is less than 255, which is the max TTL anyhow in the internet, if you reach 255, you know it's infinite, probably. Protocols like RIP have a threshold of 16. They're made for small networks. So if you reach a threshold of 16, you declare that you're at infinity. Right? So if we put all of this together, here is the answer to the question. Surprisingly, yes, Bellman-Ford does the right thing regardless of the initial conditions. You can put any kind of initial conditions, and if you run this, it will converge. If there is a path, it will converge to the true value eventually, but we're not certain that at at iteration k, it's not the distance in less than k hops. And the number of iterations you may need to do is also not necessarily bounded by n, but it will sooner or later terminate. And if there is no path, it will go to infinity. So that's the true story about Bellman-Ford. It does the right thing, always, with two caveats. If the right thing is to be infinite, then it will continue forever, count to infinity, which you need to capture and do something against it. And the other, not caveat, but the other surprising property is it will do the right thing regardless of the initial conditions, which is why distance vector works. Because now we want to do that in a network, so we will distribute it. So how do we distribute it? Well, the very simple way to distribute it is to say every node maintains an estimate of its own true distance to a given destination, and also of the information it has received from the neighbors. So every neighbor will speak to me and tell me what their distances are. I keep a record of what they said to me, and I do this Bellman-Ford computation. I look over all neighbors, what's the minimum of the cost from me to the neighbor, plus what they have advertised to me. And whenever there is a change in what the neighbors say to me, whenever I receive a new Q of j, I redo the computation. In order to redo the computation, I need to remember the values that have received from the neighbors who have not changed, if I really want to do that completely asynchronously. So I need a small routing information base which keeps a recollection of all the past values sent to me by the neighbors, the costs of all the neighbors. This is distributed Bellman-Ford that I call preliminary, because that's not the one that is implemented in distance vector routing protocol, at least not in all. And this is the very immediate mapping of the centralized to decentralized, where the only thing we have changed is now the passing of messages is asynchronous, which means we cannot be sure that there is a round number k like there was in the centralized case. It may be that some messages are exchanged more frequently, that I have received update very frequently from neighbor 5 and I've spoken to it very frequently, and other neighbors less frequently. Nonetheless, we have this theorem that says that if you can bound the time it takes to receive a message reliably from any neighbor, this works. This computes exactly the same thing as the centralized Bellman-Ford does. And one of the reasons for this robustness is related, or intuitively related, to the fact that Bellman-Ford doesn't care if you have if you have initial conditions that are wrong. So if at some point in time in the algorithm the values are completely bizarre, as soon as you keep receiving new values, you will eventually get to the final value. So this is I would say, the simplest way to distribute Bellman-Ford. Some algorithms, some distance vector routing protocols do that. If you do this, you do need to have a routing information base. You need to have this set of Q of j. Now, as I get that, I said we do that for node 1, but of course you will need to do that for every prefix n that you have heard ever. So you need to do that in parallel, not just one line here, but for every network prefix that you've heard, not just one. So I'm showing here a small simulation showing what happens here, assuming the values are given here. I'm zooming on E. E thinks its cost to 1 is 4. It also remembers that C, D, and B, C, D, and B had said 738 and infinity before. Now, if B sends a new information, B says, for example, now my value is not infinity but 1, then E will do an update by comparing the costs of going through B, which is now 1 plus 1, which is 2 plus 1, which gives 3, And this is less than the cost I had before, so I update my value here. E will update its distance, and E, and sorry, so this is the message from B to E. E has updated its distance. E can also know that which is now the direction, so it knows the shortest path by remembering who is the newest, who is the shortest, and the best neighbor was B, so it will now route through B. And in turn, after doing that, since E has changed its own distance, it will inform its other neighbors, B and C, of its new distances, and then B and C will compute, etc. This is how it will work. Now, what we have done here, and again, which is done in some routing protocol, does not satisfy the requirement to be extremely minimal. If we want to be really minimal and have no other information than your own routing table plus the cost to destination, then we could improve and get what we can call a super duper Bellman-Ford that says, after all, since I'm doing only this update, all I need to do is keep my value, Q of I, the best neighbor I have, and whenever I receive a new value from one neighbor, I compare what I had before and what is the cost of going through this new neighbor here. If this is better, I adopt it. If it's not better, what I had before was better. Does this work? I close the poll. The correct answer is a bit complicated, but the majority says B, which is true, but it depends what we call it works. It works if the initial conditions are correct and if there is no change in the network, which means that essentially it doesn't work. That means that all the beauty of Bellman-Ford that we had before, which is that if we change the initial conditions, which corresponds to saying if there's a change in the network somewhere, you simply continue the message passing and it will get back on its feet. Here it would not be the case. If we do this, it would work if you're able to reset the network whenever there's a change anywhere. So how do you reset a network? Well, you need things like OSPF is doing for that. So we don't want to have such things. So that would not be a good implementation of Bellman-Ford. That's why I called it super duper. The name was suspicious. So, anyhow. So the real Bellman-Ford that's implemented in typical distance vector protocols like RIP is this one. It's a bit more sophisticated. So we take arbitrary initial conditions. Of course, there's no reason to put initial conditions that are not the correct ones, but as we know, it's important to be robust to any arbitrary conditions. Then the update is the following. We don't keep a record of what the neighbors have said before. If we do, then we do the previous version, Bellman-Ford distributed preliminary, and that works perfectly. So the problem here is I don't want to keep this. So I have only the information of the current distance to a destination, not what the neighbors really know. But I also have another information, of course, which is who is the shortest path to the destination, which I call next hop. So next hop of I is who I believes is the shortest path to reach the destination. That's the one that's in the routing table. So all this information is in the routing table. And then when I receive a new value from a neighbor, so I am node I receive from J a new value of its distance. Then I test. If J is the next hop, I was already routing through J, and J has changed his mind for best, for better, or worse. Then I accept it. No discussion. I continue to route through J, and I say that my distance to I is through J plus the new value that J has given to me. This new value may be larger. Right? Else, if it is not coming from the next hop, I do the comparison that we said before. Right? And if this causes QI to be modified, then the next hop becomes the neighbor that caused the modification here. I don't have enough time to explain why it works, but intuitively we can see that this has a different property than the super-duper. With super-duper, whenever we receive something, we take the mean of what we had and the new thing. So we can only decrease. The distance can only get better with super-duper. So if, for some reason, the true distance has become worse because they had a failure has occurred, super-duper has no way to ever discover that. It can only increase. Here, there is a door open to increasing. If, for some reason, somebody has noticed that something has become worse, then it will say to all the nodes on which it was on the shortest path, and then the nodes that were routing through it will increase the value. Now, sooner or later, they will also receive updates from other neighbors. So if this update is not causing Q of I to be truly the shortest path distance, then sooner or later, those other values, those other updates will get us to the correct value. So there is this subtlety here. When you receive an update with RIP, with this simple form of distance vector, you have this asymmetry. If the update comes from whom you believe is the next hop, you always take it, even if it increases. If it comes from somewhere else, you look whether it's better. It's not at all obvious that this will allow the system to work, but it does. There is a theorem that says that distributed Bellman-Ford, this one here, does the job and converges to the correct value without storing anything else than the local information that is in the routing table. So let's see here, for example, what is this one? So here, the information that is stored is the cost and the next hop. So C thinks it is at a distance of 1, and the next hop is E, which is not correct, but we are, for example, in a transient phase of the algorithm. And, oops, sorry. And let's see what happens. C sends an update to E, for example. So E was also thinking that it is at a distance of 1, and the next hop is C. So because E receives the update from C, which is believed by E to be the next hop, it accepts it. So E will say, my distance is now 2. Right? So E will say, I am at a distance of 2. Right? Sooner or later, sorry, at a distance of 2, yes. So where were we? We were C sending to E. So as a result, E will send information. And so sorry, I'm giving another example here. This other example is if E receives a message from B, so E thinks that its next hop is C, so when it receives a message from B, it will adopt it and will decide that the distance is 3 and the best next hop is B here. Right? So the two cases are different. And if you take the time of going in detail through all of this, you will see that at the end, regardless of the order in which the messages are exchanged, the thing will converge to the true value here. In particular, those values that were wrong here sort of escape through other information that comes here. And the essential thing is that as long as, if we start from this initial dialogue here, C and E are stuck in a ping-pong dialogue. C believes that the best route is to E, and E believes the best route is to C, and each have the distance of 1. If we use super-duper, they will continue thinking the same way, and they're stuck here. But sooner or later, but this will not happen here, because if C gets an information for E, or E gets it from C, it will increase its information, we'll accept it. So those values will increase, a bit like the count to infinity we had before. And once the values have become large enough, then we are okay. The mean computation that is done otherwise will get us back to feet. So the problem of super-duper is if the values are less than the final values here. Voila, so that is practically all we will say. I will just illustrate how this works in practice, and this will be my last slides of the year. Here is an example of how this is run with a routing protocol like RIP. I have here a network with 5 nodes, and this is the information that every node has. It's the routing table. It's just a routing table. For example, C knows how to route to A, which is here, the prefix here. The next hop is link L2, which means the next hop is router B, and the cost is 3, 1, 2, 3 here. Compared to OSPF, with OSPF, every node has a complete map of the entire network. So here, every node knows how to go towards every destination and the distance to that destination here. If we break those two links here, and what will happen is when A and D will do the Bellman-Ford computation, now A will send to D its distance. Now there will not be just one distance, one Q value, but there will be one per destination. So in fact, there are 5 destinations here. It's a vector of distances. That's why it's called a distance vector routing protocol. So D will receive the values from A, and D will do the computation. Now, what are the computation implying? First, A has detected that there is a failure, so it sets to infinity all the distances that were to things that are not reachable, that go via a link that is dead. But there are but now it will receive from D an information about the distances. For example, A was at a distance 2 of B and was going this way towards east to this final destination. Now this link is broken, so it puts the distance to infinity. But in the meantime, it receives from D the information that the distance to B is 3. So what will this algorithm do? It will say, well, my distance, A will say, my distance to B is now 4, right? And there will be exactly what we call the count to infinity that we have seen in theory of Bellman-Ford, which will happen in practice also. So the distances will increase until eventually they reach the max value. So we'll see. So A and D will detect that they're not connected to all those destinations only by counting to infinity. I said only by counting to infinity. There are a number of ways to detect that such loops are happening before counting to infinity. They are called route poisoning. And this is an optimization that I will leave to you to discover if you like. Voila, that's the end. Thank you very much. And see you tomorrow for next and last step. Thank you.